In this video, we're going to have a look at another example of an application of a first-order differential equation. And this one involves a real-world problem with rates of change, and we will apply a first-order differential equation to model this situation. Now, basically, we're going to have a tank, 100 litres of water with a salt solution in it, and we're going to then add another salt solution to it and look at the rate at which salt builds up in the tank. And then in the second part of this problem, we'll look at a situation where liquid flows out and the change in the amount of salt left in the tank as it does so. All right, so let's start with this situation. So we've got a tank, initially contains 15 kilograms of salt in 100 litres of water. So you can imagine a big container, and you've got oh, I'd like to have that in red, wouldn't I? And we've got a solution in here. Okay, we've got 100 litres of water. Okay, and we have 15 kilograms of salt dissolved in there. And into this tank is flowing at a rate of 4 litres per minute a salt solution containing 2 kilograms of salt per litre. So there's going to be another flowing into this. Another solution which contains 2 kilograms of salt per litre of water, so an incredibly salty solution. Okay, now assuming the mixture is kept uniform, so we're going to make this assumption that it doesn't pile up in one corner. We're going to assume that it's evenly mixed throughout. Assuming that the mixture is kept uniform and that after T minutes, m kilograms of salt remains dissolved in the tank. Okay, so construct an appropriate differential equation expressing dm, that's the amount of salt in kilograms, how the change in m with respect to t as a function of t, if the mixture A remains in the tank, i.e. the tank fills up instead of emptying out. So we're going to start off with a tank, 100 litres of water with 15 kilograms of salt dissolved into it. Into that we're going to pour another solution containing 2 kilograms of salt per litre of liquid, and that's going to instantaneously and evenly mix. Okay. Now we're interested in the change in the amount of salt in kilograms with respect to time. We want dm dt. M is the amount of salt in kilograms and t is time in minutes. Okay, generally with these problems there's going to be something like dm dt has an input rate minus an output rate. Okay, because dm dt is a rate of change. What rate of change is happening? Well, there's an input rate and there's an output rate. Now sometimes one of these will be missing. Maybe there's only an input rate, as in part A here, or maybe there's only an output rate, as in part B. Okay, so dm dt is the amount of salt added per litre times the number of litres per minute. Okay, and then likewise the output rate will be the amount of salt lost per litre, okay, times number of litres run off per minute. So if we were to write this out with dimensions, we'd have dm, okay, dv times dv dt. Notice that dv's cancel and we're left with dm dt. So the units are consistent. The output rate is 0 because solution is only flowing into the tank and not out. Okay, so it's coming in at the rate of 2 kilograms per litre times 4 litres per minute. Okay, that's what we were given. So dm dt is 8 kilograms per minute. Okay. Solving this, we have, well, we could separate the differentials. Dm is 8 dt. Integrate both sides. You have dm integral 8 dt plus c, because this m is 8t plus c. Now at t equals 0, and this is the constant part here, because remember we started with some salt in the container there. Okay, this is the mass at time t. Now at t equals 0, we have m is 15 kilograms. Okay, so if we put 0 where the t is, that part disappears and we're left with m, which is 15, is equal to c. So c is 15 and m is 8t plus 15. That's the mass of salt in the tank at time t. Okay. All right, now the tank cannot go on filling indefinitely, so the domain of t must be limited. Okay, it's not an infinite container. There must be a limit at some point it's full. So let the volume of the tank be F litres, capital F litres. All right, hence the total volume at time t, given that 4 litres is added every minute, must be 100 plus 4t litres. Initially we start off with 100 litres, and then we're adding 4 litres every minute. Okay, so we must have 100 plus 4t. Now 100 plus 4t must be equal to or less than f. Okay, whatever f is, however many litres it is for the tank. So rearrange that, we have 4t as f minus 100, or t is equal to or less than f minus 100 on 4. Okay, so that's the limitation on the domain. T must be equal to or less than f minus 100 over 4. All right, let's look at the second part of this now. Now, the solution flows out at the rate of 7 litres per minute, while the input rate is 0. Okay, so the change in the amount of salt kilograms with respect to time is dm dt is the input rate minus the output rate, because dm dt is a rate. So this must be input rate minus output rate. There's only two ways, going in and going out. Okay, so dm dt is the amount of salt added per litre times the number of litres per minute, minus the amount of salt lost per litre, okay, times number of litres run off per minute. Okay, so input rate dm dv times dv dt, well, that's all zero. There's no input rate. Nothing's being put in. The solution is simply flowing out of our tank. Okay. The output rate, dm dv times, that's the kilograms per litre times litres per minute, is m on 100 L minus 7 times T L. That's kilograms per litres times 7 on litres per minute. So that gives us m is 100 over, m over 100 minus 7t kilograms per litre. Here's our litres here. Okay, times 7 litres per minute is 7m on 100 minus 7t kilograms per minute. Okay, the litres here cancel, we're left with kilograms per minute. Okay. All right, because if you remember here, 7 litres per minute is going out. So you have 100 litres, this bottom bit here, just 100 litres minus 7 litres. Okay. Okay, going 7t, 7 litres per minute times the time for each minute. Okay, because obviously when this is 0, nothing can flow out. So when 7 times t is equal to 100, nothing more can flow out. It's all gone. Okay, so I hope that bit there is clear. Okay. Now, note while the volume is decreasing over time as water runs off, that is 100 minus 7t litres per minute. Hence dm dt, 0 input rate, minus an output rate, 7m on 100 minus 7t. So let's solve that. Dm dt is minus 7m on 100 minus 7t. And we have here dm is minus 7m on 100 minus 7t. Again, just splitting the differentials here times dt. Dividing through by m, dm on m is minus 7 on 100 minus 7t dt. Integrating both sides, we have 1 on m dm equals the integral minus 7 on 100 minus 7t, and plus, of course, constant of integration, which I'll write down here. Okay, the antiderivative of 1 on m will be natural log of m is equal to the integral of this. Okay, and again, same thing, we'll do the natural log on this side. So natural log of m is equal to the natural log of 100 minus 7t. When you differentiate that, you get minus 7 over 100 minus 7t, so that exactly matches, plus our constant. Okay, let's subtract the natural log term, first term on the right there, the natural log term, bring that over the other side. Okay, because we can use the log laws when we do that, which gives us the natural log of m over 100 minus 7t equals our constant. Exponentiate both sides, it gets rid of the natural log. E to ln of that will just give us the argument, m over 100 minus 7t. E to the c, okay, is just going to be a constant. We're going to give it another name before long. Okay, so what that means is now we have m is equal to e to the c times, in parentheses, 100 minus 7t, and m, and what we're going to do, that e to the power of c, we're just going to label it more conveniently just the constant k, because that's all it is, just a constant. So m equals k times 100 minus 7t. All right, now we have at the start at t equals 0, we had 15 kilograms when we started. Okay, so here we put 15 is equal to, we're going to substitute that into here. We substitute into this one. Okay, well, t equals 0, that bit drops off, and we have 15 is equal to k times 100, or k is 15 on 100, or k is 3 on 20. Okay, or 0.15 is probably easy to deal with, but anyway, m equals 3 on 20 times, in parentheses, 100 minus 7t. If we plot this, okay, we'll see how long it takes us. Now, across the bottom here, we're going to have time, and we're not going to have this bit underneath here, that's for sure. Okay, because we can't have negative mass for obvious reasons, so please don't plot that. In hindsight, I wish I'd picked that up earlier and not plotted that. Okay, and this at some time is going to go to 0. All right, the mass will go to 0 at closer to about 14 minutes or something. All right, and that is that.